April 12, 1930. Power Jets Limited Workshop, Rugby, England. The high-pitched whine had been building for 17 seconds when senior technician Harry Edgley noticed something catastrophically wrong. The experimental compressor, spinning at 12,000 revolutions per minute, had begun vibrating in patterns that violated every principle of mechanical engineering he understood. Through the observation window, 23-year-old Frank Whittle stood transfixed, his hand hovering over the emergency shutdown switch. The test they had prepared for 6 months was supposed to validate a theoretical concept that every established aerospace engineer in Britain had declared impossible. Instead, the machine was tearing itself apart. Then Edgley made his mistake. In the chaos of alarms and shouting, he reached for what he believed was the fuel cutoff valve. His hand, slick with perspiration, slipped past the red-handled emergency stop and instead grabbed the blue-handled throttle. He twisted it counterclockwise, hard. What happened next should have been catastrophic failure. The fuel flow, instead of stopping, increased by 40%. The compressor, already screaming at dangerous speeds, accelerated beyond anything the calculations predicted. The temperature gauge needle slammed against its maximum reading of 1,000 degrees Fahrenheit and kept climbing, but the vibrations stopped. The chaotic shaking that had threatened to destroy the machine suddenly smoothed into a steady, powerful hum. The exhaust temperature stabilized at 1,200 degrees, and from the tailpipe, a jet of superheated gas erupted with such force that it shattered 3 windows across the workshop. Whittle's face went pale as he checked the instruments. The thrust gauge, which they had optimistically hoped might register 50 pounds, was reading 240 pounds. Impossible. The compressor efficiency, which theory suggested should peak at 60%, was showing 82%. Inconceivable. Edgley stared at his trembling hand, still gripping the throttle he had grabbed by mistake. In his panic, in his fumbling error, he had accidentally discovered the operating principle that would revolutionize aviation. He had stumbled upon the solution to a problem that had baffled the world's greatest engineers for decades. This is the story of how one technician's ridiculous mistake in a cramped British workshop created the jet engine, transformed aerial warfare, enabled supersonic flight, and accidentally launched humanity into the jet age. It is the story of how blind panic and a slippery hand accomplished what years of careful calculation could not. The rejection began long before that April morning. In October 1926, Frank Whittle was a 16-year-old flight cadet at Royal Air Force College Cranwell when he submitted his thesis titled Future Developments in Aircraft Design. The paper, required for graduation, proposed something that senior instructors found absurd. Whittle calculated that aircraft could achieve far greater speeds and altitudes if they abandoned propellers entirely. Instead, he proposed using a gas turbine to generate thrust directly through exhaust gases. His mathematics suggested aircraft could reach altitudes of 50,000 feet and speeds of 500 miles per hour, more than double any existing performance. His thesis advisor, squadron leader Henry Browncave, wrote across the cover in red ink, "Interesting speculation, but fundamentally impractical. The temperatures and pressures required would destroy any known materials. Stick to realistic engineering." The thesis received a bare passing grade, but Whittle couldn't abandon the idea. Throughout his training as a pilot, through his posting to fighter squadrons, during every spare moment, he refined his calculations. By 1929, he had developed detailed specifications for what he called a turbojet engine. The concept was elegantly simple. A compressor would squeeze incoming air to high pressure. Fuel would be injected and ignited in a combustion chamber. The expanding hot gases would drive a turbine connected to the compressor, while the remaining exhaust provided thrust. No propeller, no mechanical limitations, pure jet propulsion. In January 1930, Whittle filed British Patent Number 347-206 for improvements relating to the propulsion of aircraft and other vehicles. The Patent Office accepted it without understanding its significance. The British Air Ministry, however, rejected it outright. Air Commodore Geoffrey Salmon's response, dated March 3, 1930, was devastating. The turbojet concept, while theoretically interesting, suffers from insurmountable practical difficulties. The temperatures required would melt steel. The fuel consumption would be prohibitive. The weight of necessary components would prevent flight. We see no military application and recommend the inventor pursue more conventional approaches. Germany, meanwhile, was listening. Unknown to Whittle, a physics student named Hans von Ohain at Göttingen University had independently conceived an almost identical concept. And unlike Whittle, von Ohain had a patron. Ernst Heinkel, the aircraft manufacturer, saw military potential and provided unlimited funding. Whittle, by contrast, struggled in poverty. The Royal Air Force, uninterested in his invention, assigned him to routine duties. His patent, which cost £5 annually to maintain, lapsed in 1935 when he couldn't afford the renewal fee. Any nation could now use his design without compensation, but in 1935, two former RAF officers, Rolf Dudley Williams and James Tinling, approached Whittle with an offer. They had found investors willing to risk £2,500, approximately $200,000 today, to build a prototype. It was barely enough, but it was something. Power Jets Limited was incorporated on March 27, 1935. The company consisted of Whittle, working after his RAF duties, two investors with no engineering knowledge, and a leased workshop in Rugby with outdated equipment. They were attempting to revolutionize aviation with less funding than a small automobile repair shop. The technical challenges were staggering. Whittle needed to create a compressor that could handle air at pressures and temperatures never before achieved. He needed combustion chambers that wouldn't melt. He needed turbine blades that could survive in conditions that destroyed conventional metals within seconds. British Steel Works, approached about manufacturing the compressor, responded that the tolerances Whittle specified were impossible with existing machinery. Precision Castings refused to attempt the turbine blades, stating the alloys required didn't exist. Lucas Aerospace declined to develop the fuel injection system, calling it suicidal. Whittle was forced to use whatever components he could scavenge or afford. The compressor was built by British Thomson Houston using modified steam turbine technology. The combustion chamber was hand-welded from standard boilerplate steel. The turbine blades were cast from a nickel alloy developed for locomotive engine valves, not aerospace applications. By April 1930, after 5 years of rejection and ridicule, after exhausting his investors' patience and his own health, Whittle had assembled something that looked less like the future of aviation and more like a plumber's nightmare. Pipes, valves, and chambers connected in ways that violated every aesthetic principle of engineering. Harry Edgley, the senior technician hired to operate the test rig, privately told his wife the contraption would blow us all to kingdom come. The workshop staff had taken to calling it Whittle's folly. Even Whittle himself, in his private notes, admitted doubts about whether the fundamental concept was sound. The morning of April 12th dawned cold and gray. Whittle arrived at the workshop at 5:30, unable to sleep. The test was scheduled for 9 o'clock, after they had checked every connection, every valve, every gauge for the 100th time. The prototype, officially designated the Whittle Unit, or WU, sat on its test stand like a metal sculpture of industrial chaos. It weighed 800 pounds, far heavier than calculations suggested it should. The compressor, 16 inches in diameter, was connected by a shaft to a turbine of similar size. Between them, 10 combustion chambers arranged in a circle were supposed to generate the heat that would make the whole system work. Edgley walked through the startup checklist with mechanical precision. Fuel pressure, normal. Compressed air supply for starting, ready. Cooling water flow, adequate. Instrumentation, functioning. Fire suppression, armed. Ambulance, on standby, per insurance requirements. At 8:55, Whittle gave the order to begin. Edgley opened the compressed air valve that would spin the compressor for initial startup. The unit began to rotate, slowly at first, then faster. At 3,000 revolutions per minute, Whittle signaled to introduce fuel. The ignition was supposed to be smooth. Instead, the combustion chambers lit with a bang that shook the entire building. Flames shot 4 feet from the tailpipe. The thrust gauge jumped to 70 pounds, then fell back to 20. The unit continued accelerating, but unevenly, shaking violently. At 8,000 revolutions per minute, a grinding noise emerged from the compressor bearing. At 10,000, the vibration became visible. The entire test stand rocking. At 12,000, Edgley shouted, "She's coming apart." Whittle hesitated. They had never achieved 12,000 revolutions per minute before. The data, if they could capture it, would be invaluable. He watched the gauges climb. 12,500. 13,000. The vibration was now so severe that instruments were falling off their mounts. "Shut it down!" Whittle finally yelled. But the noise was deafening. Edgley couldn't hear. He saw Whittle's gesture toward the control panel and reached for what he thought was the emergency stop. His hand, made clumsy by thick leather gloves and adrenaline, missed the red valve and grabbed the blue throttle instead. He twisted hard. expecting fuel flow to cease. Instead, the engine note changed instantly. The scream became a roar. The vibration smoothed, and the thrust gauge needle swept past 100, past 150, past 200 pounds. For 3 seconds, nobody moved. They stared at instruments showing readings that shouldn't exist. Then Whittle grabbed the actual fuel shutoff, and the unit spooled down, the turbine's dying whine lasting nearly a minute as internal temperatures slowly decreased. In the silence that followed, Edgley slowly removed his gloves and stared at his hands. "I grabbed the wrong valve," he said quietly. "I increased fuel instead of cutting it." Whittle didn't respond immediately. He was studying the data recording drums, mechanical devices that had traced the engine's performance on suited paper. The curves showed something extraordinary. When Edgley had accidentally increased fuel flow, the compressor had achieved a pressure ratio of 4.2 to 1. The exhaust temperature had stabilized at 1,300 degrees, and most significantly, the system had reached a self-sustaining state where the turbine extracted just enough energy to drive the compressor while still producing massive thrust. "You found the operating point," Whittle said, his voice distant. "We were running too lean. The combustion wasn't complete. When you increased fuel flow, you achieved stoichiometric combustion, complete burn. That's why the vibration stopped. That's why thrust increased." Over the following weeks, they conducted 19 additional tests, carefully mapping the engine's performance. Each test confirmed what Edgley's mistake had revealed. The jet engine didn't operate efficiently at the conservative fuel flows Whittle's calculations had specified. It needed to run hot, far hotter than conventional engineering wisdom suggested was safe. The breakthrough was documented in PowerJet's Technical Report No. 7, dated May 19, 1930. The report, written by Whittle, acknowledged explicitly that operating parameters determined through trial exceed calculated safe limits by significant margins. However, experimental results confirm sustained operation is achievable. Translation: the engine worked because it violated the rules they thought governed it. The news spread slowly through Britain's aerospace community. Most engineers remained skeptical. Sir Henry Tizard, chairman of the Aeronautical Research Committee, visited the Rugby workshop in June 1930 and declared the device interesting but impractical for aircraft use. The weight, he calculated, would prevent any aircraft from achieving useful performance. But a few understood. Air Commodore Roderick Hill, Director of Scientific Research at the Air Ministry, recognized potential and authorized funding of £2,000, barely enough to continue development. Hill's support would prove crucial, though he faced intense criticism from superiors who considered the jet engine a distraction from proven piston technology. Meanwhile, in Germany, Hans von Ohain was solving similar problems with far greater resources. Heinkel had provided a dedicated team of 40 engineers and access to Germany's best metallurgists. By August 1937, von Ohain's He S-3B engine achieved sustained operation. On August 27, 1939, the Heinkel He 178, powered by von Ohain's engine, flew for 5 minutes at Rostock-Marienehre Airfield. It was the world's first jet-powered aircraft flight, achieving speeds of 380 miles per hour. Germany had won the race to practical jet aviation. The news reached Britain on September 2, the day after Germany invaded Poland. Suddenly, the jet engine wasn't an interesting curiosity. It was a potential war-winning weapon in enemy hands. The Air Ministry's response was dramatic. Whittle, still a serving RAF officer, was promoted to squadron leader and given unlimited access to resources. PowerJets received contracts worth £100,000, and critically, they were provided with a team from Rover Cars to scale up production. The partnership with Rover was disastrous. The automotive engineers, accustomed to piston engines, couldn't grasp jet engine principles. They made improvements that destroyed efficiency. They substituted materials without understanding thermal requirements. They insisted on manufacturing shortcuts that caused catastrophic failures. By 1941, the relationship had collapsed entirely. Rolls-Royce, Britain's premier aero engine manufacturer, took over. Their engineers, led by Stanley Hooker, brought world-class metallurgy and precision manufacturing. Progress accelerated dramatically. Now would be a great time to subscribe to the channel if you're enjoying this deep dive into one of aviation's most remarkable origin stories. We explore forgotten moments in history where mistakes, accidents, and chance discoveries changed everything. Hit that subscribe button and bell icon so you don't miss future videos about the unexpected ways technology evolves. The first British jet aircraft, the Gloucester E-28/39, flew on May 15, 1941, from RAF Cranwell. Whittle's jet engine, designated the Power Jet's W1, powered the aircraft to speeds of 335 miles per hour. It was slower than Germany's jet, but it proved the concept worked. But transforming a prototype into military hardware required solving problems that made the original development seem simple. The early engines lasted only 10 hours before requiring complete rebuilding. Turbine blades cracked from thermal stress, combustion chambers burned through, fuel pumps failed, bearings seized. The metallurgical challenges were unprecedented. Turbine blades operated at temperatures of 1,400 degrees Fahrenheit while spinning at 14,000 revolutions per minute. The centrifugal force created stresses of 40 tons per square inch. No existing metal could survive these conditions for long. Henry Wigan and Company developed a new nickel-chromium alloy called mnemonic, specifically for turbine blades. It could withstand 1,500 degrees for hundreds of hours. This single metallurgical breakthrough made practical jet engines possible. The Americans entered the picture in April 1941. General Henry Hap Arnold, commanding general of the U.S. Army Air Forces, visited Britain and witnessed the Gloucester E-28 fly. He immediately recognized the jet engine's potential and requested complete technical details under Lend-Lease agreements. Whittle personally traveled to America in June 1941, carrying complete drawings and specifications. He met with engineers from General Electric, who would manufacture the engine under license as the IA. The American industrial machine, once engaged, moved with breathtaking speed. General Electric built a complete jet engine in 6 months, something that had taken Whittle 6 years. They didn't understand the theory better, but they had resources Whittle never possessed. Precision casting facilities, advanced metallurgy labs, unlimited funding, and crucially, freedom from bombing raids that disrupted British production. The Bell P-59 Aerocomet, America's first jet fighter, flew on October 1, 1942. It used 2 GE IA engines, direct descendants of Whittle's design. While the P-59 proved disappointing in performance, it established American jet engine production capability. Germany, meanwhile, had rushed the Messerschmitt Me. 262 into production. By late 1944, over 1,000 had been built. With top speeds of 540 miles per hour, they were untouchable by Allied piston engine fighters, but critical material shortages meant engines lasted only 10 to 25 hours before failure. The contrast revealed fundamental differences in approach. German engines used axial flow compressors, more efficient but far more complex to manufacture. British and American engines used Whittle's centrifugal compressor design, less efficient but simpler and more reliable. In wartime, reliability mattered more than theoretical efficiency. The jet engine's impact on World War II was ultimately limited. Germany's jets came too late and in too few numbers. Britain's Gloucester Meteor entered service only in July 1944, shooting down Von flying bombs but seeing little combat against aircraft. America's jets remained developmental, but the post-war impact was revolutionary. By 1950, every major air force was transitioning to jets. Piston fighters, which had dominated aviation for 40 years, became obsolete almost overnight. The jet age had arrived. The technology proliferated rapidly. Rolls-Royce sold Nene engines to the Soviet Union in 1946, a decision Britain's government would regret when Soviet-built copies powered MiG-15 fighters in Korea. Pratt & Whitney developed the J-57, powering the B-52 bomber that remained in service for 70 years. General Electric's J-79 powered supersonic fighters that broke sound barriers routinely. Commercial aviation followed. The de Havilland Comet, first jet airliner, entered service in 1952. The Boeing 707 followed in 1958, revolutionizing travel. Jets cut transatlantic flight time from 18 hours to 7. They made air travel affordable for millions. They shrank the world. By 1970, jets carried 200 million passengers annually. By 2000, over 1.5 billion. Today, over 4 billion passengers fly on jets yearly. The technology that began with Harry Edgley's panicked grab for the wrong valve now transports half of humanity through the air each year. Frank Whittle received a knighthood in 1948, belated recognition for his achievement. But Power Jets Limited was nationalized in 1944, and Whittle received only £100,000 in compensation, roughly $5 million today, for inventing technology worth trillions. He moved to America in 1976, becoming a professor at the U.S. Naval Academy. In lectures, he often told the story of that April morning in 1930, of Edgley's mistake, of blind panic leading to breakthrough. The greatest discoveries, he would say, often come from failures we don't expect. Hans von Ohain, who had developed his jet engine independently, met Whittle in 1978. The two men, who had raced to create the same invention on opposite sides of a war, became close friends. Von Ohain told interviewers that Whittle's fundamental design was more elegant, more practical, and more influential on subsequent development. Harry Edgley, the technician whose mistake changed aviation, lived in quiet obscurity. He continued working for Power Jets through the war, then took a position at Rolls-Royce as a test engineer. He retired in 1968 and died in 1985, having given only 2 interviews about his role. In a 1976 interview with Aviation Week, Edgley was asked if he understood, in that moment of panic, that he had made history. His response captured the accidental nature of breakthrough. "I thought I was killing us all. I grabbed the wrong valve because I was terrified." Later, they called it brilliant intuition. It was just a mistake. But I suppose that's how progress happens. Someone makes a mistake, and if they're very lucky, it works. The jet engine's development reveals profound truths about innovation. First, that revolutionary ideas face inevitable rejection from established experts. Every aerospace engineer in Britain had sound technical reasons for dismissing Whittle's concept. They were wrong not because they were stupid, but because they couldn't imagine solutions to problems that seemed insurmountable. Second, that breakthroughs often come from unexpected sources. Edgley wasn't an engineer. He was a technician following orders. His contribution was pure accident, yet that accident revealed operating principles that years of calculation had missed. Third, that innovation requires persistence beyond rationality. Whittle spent 9 years pursuing an idea that everyone told him was impossible. He exhausted his health, his finances, and his credibility. Only irrational stubbornness kept him going. Fourth, that real-world testing reveals truths that theory cannot predict. Whittle's calculations were wrong about optimal operating conditions. The engine worked, but not for the reasons he expected. Only empirical testing revealed the truth. The technical specifications that emerged from that accidental discovery established principles still governing jet engines today. All modern jets use essentially the same cycle: compression, combustion, expansion through a turbine, and thrust from exhaust. The temperatures, pressures, and efficiencies have increased enormously, but the fundamental concept remains. Whittle's modern jet engines achieve compression ratios of 40:1 versus Whittle's 4:1. They operate at turbine inlet temperatures of 3,000 degrees Fahrenheit versus his 1,300. They produce 40,000 pounds of thrust versus his 240, but they're still recognizably descendants of the device that almost destroyed itself in a rugby workshop. The materials science advances required to make jets practical drove broader technological progress. Pneumonic alloys developed for turbine blades found applications in nuclear reactors, chemical plants, and rocket engines. Precision casting techniques developed for complex turbine geometries enabled new manufacturing across industries. Computational fluid dynamics developed to model compressor flow became essential tools in countless fields. The economic impact of jet engines defies measurement. Commercial aviation generates $2.7 trillion annually in economic activity. It employs 65.5 million people globally. It enables globalization, international trade, rapid medical response, and cultural exchange on scales impossible before jets existed. Military aviation was revolutionized even more profoundly. Jets enabled supersonic flight, allowing interceptors to reach threatened areas in minutes rather than hours. They enabled strategic bombing at altitudes and speeds that made defense nearly impossible. They enabled reconnaissance satellites launched by jet-powered rockets. If you're fascinated by these pivotal moments where accidents and mistakes shaped technology and history, make sure you're subscribed. We'll be exploring more stories where human error, panic, and chance created world-changing innovations. Click subscribe and ring the notification bell so you catch every episode. The counterfactual questions are intriguing. What if Edgley had grabbed the correct valve that morning? Would Whittle have eventually discovered optimal operating conditions through systematic testing? Almost certainly, but months or years later. What if the Air Ministry had funded Whittle adequately in 1930? Britain might have entered World War II with operational jets, potentially changing the war's course. What if Germany had kept its lead in jet technology? Hitler's interference, demanding that the Me-262 be modified as a bomber rather than deployed as a fighter, delayed its effective use by crucial months. Properly deployed in late 1943, German jets might have prevented Allied strategic bombing, prolonging the war significantly. What if the Soviet Union had developed jets independently rather than copying British designs? The Cold War's military balance might have differed substantially. Soviet aviation technology lagged Western capabilities for decades, partly because they started from copied designs rather than fundamental understanding. But history followed the path it did, shaped by Edgley's mistake and countless other accidents, decisions, and circumstances. The jet age arrived not through careful planning, but through chaotic development, driven by war, national rivalry, and individuals who refused to accept expert consensus about what was possible. Frank Whittle died on August 9, 1996, at age 89. His obituaries noted that he had lived to see his invention transform human civilization. Over 2 billion people had flown on jet aircraft by then. Whittle himself had flown supersonic in jets based on his principles. He had witnessed moon landings enabled by jet-derived rocket technology. In his final interview, conducted 3 months before his death, Whittle reflected on that April morning 66 years earlier. Harry Edgley's mistake taught me that nature doesn't care about our theories. The universe operates according to its own rules. Our job is to discover those rules, not to insist that nature conform to our expectations. Sometimes discovery requires abandoning everything you think you know and paying attention to what actually happens, even when it contradicts your calculations. Hans von Ohain died on March 13, 1998. His last public statement praised Whittle as the true father of the jet age. Frank Whittle had the original concept. He faced rejection and poverty but persisted. I had resources and support. History should remember him as the pioneer. I was merely a successful follower. The workshop in Rugby where the breakthrough occurred was demolished in 1962 to make room for a shopping center. No plaque marks the location. The actual Whittle unit from that April test was preserved and is displayed at the Science Museum in London, a tangle of pipes and chambers that looks more like sculpture than technology. Modern visitors often express surprise that something so crude revolutionized aviation. But that crude device, running at temperatures everyone said would destroy it, operated at efficiencies everyone said were impossible, all because a terrified technician grabbed the wrong valve. The story of the jet engine's creation contains lessons that extend far beyond aviation. It demonstrates that expertise, while valuable, can blind us to possibilities outside conventional understanding. Every expert who rejected Whittle was correct according to existing knowledge. They failed to imagine that existing knowledge was incomplete. It shows that breakthrough innovations often come from outsiders. Whittle was an RAF pilot, not an academic researcher. His lack of formal credentials in thermodynamics may have freed him to consider approaches that trained specialists would dismiss. Sometimes not knowing what's impossible enables achieving it. It reveals that serendipity plays a larger role in progress than we admit. Edgley's mistake was pure chance, but chance favors prepared minds. Whittle recognized immediately what the accident revealed because he understood the underlying principles deeply enough to interpret unexpected results. It proves that failure is not the opposite of success, but often its prerequisite. Whittle failed repeatedly for 9 years. Each failure taught lessons that made ultimate success possible. Had he succeeded immediately, he might not have explored parameter space widely enough to find optimal solutions. Most profoundly, it shows that progress often requires operating beyond safety margins. The jet engine works precisely because it runs hotter, faster, and harder than conservative engineering would permit. This principle applies broadly. Revolutionary advances usually require accepting risks that seem unacceptable until the advance proves itself. Today, when you board a jet aircraft, you're trusting your life to technology that began with a mistake. That Airbus or Boeing operates reliably because thousands of engineers have spent 80 years refining principles discovered when a panicked technician grabbed the wrong valve. The engine's roar at takeoff, the smooth acceleration through Mach 0.8 at 35,000 feet, the ability to cross oceans in hours rather than days, all of it traces back to that April morning when everything went wrong in exactly the right way. The jet engine stands as perhaps the 20th century's most significant transportation innovation. It has enabled globalization, connected distant cultures, made rapid humanitarian response possible, and allowed more humans to experience flight than walked the earth when Whittle was born. And it began with a ridiculous mistake, a wrong valve, a panicked grab, an accidental increase in fuel flow that should have been catastrophic, but instead revealed truth. Harry Edgley's hand slipped, and aviation was never the same. In the end, the story of the jet engine is a story about human progress. We don't advance through steady, predictable steps, guided by perfect knowledge. We advance through chaos, mistakes, and accidents that reveal unexpected truths. We advance through individuals who persist despite rejection. We advance through moments of panic that somehow become moments of discovery. Frank Whittle designed the future. Harry Edgley accidentally discovered how to build it. Together, they created technology that has shaped the modern world as profoundly as electricity, antibiotics, or computers. The next time you fly, remember that you owe your journey to a mistake, to a technician who grabbed the wrong valve at the worst possible moment, to blind panic that became brilliant discovery, to failure that became the foundation of an industry. The ridiculous mistake that created the jet engine proves that sometimes, just sometimes, the wrong decision at the right moment changes everything. Harry Edgley's hand slipped, the throttle turned, the engine roared, and humanity entered the jet age. All because someone grabbed the wrong valve.